Hey, this is Trek, and welcome back to my series on calculus. This is the fourth video where we're going to go over the shortcuts and sort of simplifications of derivative-based problems. So let's just jump into it. We have our first setup here where we're going to talk about what the derivative of a constant is. We actually saw a little bit of this in the previous video, but we're going to cover it in more detail here. Basically, if we have a function for which the value is a constant with respect to x, then its derivative is 0. And let me turn this on. So we have the function f of x equals 5, or y equals 5, as the case might be, some constant. And it's a horizontal line, so right here the derivative is a flat line, and you got a slope of 0, so it's going horizontal. Over here you also have a slope of 0. In fact, the slope is 0 at any given point. So if we put this here, we should get a blue line going along 0, because at any point along this horizontal line, the slope of the line is 0. Simple enough, but before we move on, I want to make sure I cover an important detail as we get further and further into calculus, and that's that this constant here that we are talking about, this k, f of x equals k, that's not necessarily a true constant. What it is a constant with respect to x. It could, for example, be something like if we have a function which is in terms of both x and y, and the function is something like y squared plus 5, its derivative with respect to x is still 0 because it is not varying with respect to 0. It is only varying with respect to y. So whenever we talk about constants in the next few videos and later on in the course, then remember to keep that in mind, that when I say constant, I just mean with respect to a certain variable, as in it has no variation as that variable changes. Alright, so let's move on to our first true rule, which is what I call the coefficient rule. And simply put, if you have a constant times a function, like if our function f of x has the form constant times another function, then its derivative is that constant times the derivative of that function. And remember, the constant is with respect to a certain variable, in this case x. Constant with respect to x. So let me give you an example of what that might look like. For example, we have something like f of x is equal to 3 times a function, let's call it x to the 6th. This right here is a function, and here we have a constant, so our derivative should be equal to 3, we'll call this g of x, times g prime of x. And we'll cover what that actual derivative is later on, but for now I just want you to get that you can kind of phase out constants and just leave them out of the calculation of the derivative and multiply them to the final result. I have an example here of f of x equal to 3x. So a simple function goes over 1 up 3, or over 2 up 6 in this case, and its derivative should be 3 times the derivative of x, which I will tell you right now is actually just the number 3. We'll cover that rule next, but it's just important to note that 3 is the number we ended up with, and it ended up being multiplied by the derivative of x. And next up, I just wanted to go over real quick. This is an example of what I mentioned in the previous example, where you have 4 times z times x. 4z is a constant with respect to x because it's not varying with x. So we could say that our k in our description up here could be equal to 4z in this case. So our final derivative would be equal to 4 times z, which is 2, times the derivative of x, which is 1, as we briefly shown up there. So we should have a number of 8. Okay, let's move on to the next one. Okay, so this is the power rule. This is a very important one. It gets used a lot. Basically, if you have a function of the form f of x is equal to x to the n, then our derivative is equal to n to the x to the n minus 1. And this one we saw a lot during the last few videos. A lot of those were power rule evaluations. Let me give you an example of one, like x squared, which we did in the very first video. Yeah. And if you recall, our derivative that we came to was 2x by doing our normal evaluation. So we take this 2. This is equal to n in this case. So that's equal to n. And we bring it down. So we do 2 times x. Then we do n minus 1 to the 1, which is equal to 2x, which is what we got in our first and third video. We'll bring this up so you can see the examples. So here we have x squared. And our derivative should be 2x, oops, which it is, over 2 up 4, 2x. Alright, and we're going to do a little bit more advanced example, because this is really a common one. I really want you to follow what it's talking about. So we have g of x is equal to x to the negative 2. Now this applies, you can use the power rule on anything that isn't, you can use it on anything that isn't x to the 0. So you can use it on x to the 1 and x to the negative 1 and any integer value or even non-integer value besides that one. So here it is. We are going to get g prime, or the derivative of x. You might hear me call this g prime, or this symbol here prime, or f prime. It just means the same thing. Anyway, we're going to bring this negative 2 down, negative 2, and then we're going to subtract 1, so to the negative 3. So negative 2x to the negative 3. That's our derivative in this case. We actually did see an instance of this in the previous one. I think it was, oh yeah, it was square root of 3x. Let me show you that one again real quick. So if our f of x is equal to the square root of 3x, well, that's the same thing as 3x to the 1/2. And let's actually, because we haven't talked about this yet, I'm gonna take out the 3. So f of x is equal to the square root of x, which is equal to x to the 1/2. And that would make our f prime of x equal to, we bring down the 1/2, so 1/2 times x, then 1/2 minus 1 is negative 1/2, which is equal to 1 over 2 times the square root of x. If you recall, in our previous video, we got 1 over 2 times 3x, 1 over 2 times the square root of 3x. Same mechanic. Let's move on to our other example here on this page. So we have, oh, I didn't get to show you guys this. So here we have x to the negative 2, and our derivative, which we determined was negative 2 times x to the negative 3rd, so it should be an uneven function. It should go up and down. Yep, see? Alright, let's move on to the next example. And again, this is a really important one. You should get familiar with this one. Spend some time practicing it outside of watching this video. Okay, the sum rule. Sum rule is also very important. We use it a lot. It's probably the third most used rule, something like that. But the gist of it is that if you have some function, say f of x, and it has the form of another function plus some other function, or any number, you could just keep going, like, you know, however many different terms you have, then its derivative is, or its f prime is equal to simply the derivative of each term plus each other, with however many they are. You just take the derivative of each term in sequence, or in turn. So let's go through our example of this. We have f of x is equal to x squared plus 3x plus 2. Turn it on. Looks kind of like the x squared graph. And using what we just learned, we take the derivative of each one in turn. So let's do this one first. So the derivative of this, as we learned in the previous example, is the power rule. So we bring down the 2, so we get 2x, and we subtract 1, so we just end up with 2x to the 1. All right, then we move on. Oh, I can explain what the derivative of x is now. Remember, this is the coefficient rule, so we can just kind of ignore this 3 and multiply it at the end. But the derivative of x, which we can write as x to the 1, is you bring down the 1, and we're going to bring down this 3 later on, and then you subtract 1, so you get x to the 0, which is 1. So times 1 times 3, so you bring this out. So this is just 3 here. Alright, and the third term is 2. So what's the derivative of 2? As we learned in our first example, the derivative of any constant is 0. So we end up with 2x plus 3. Okay. Good job, everyone. 2x plus 3 should go right through here and should end up going to here, something like that. Let's turn it on. Yep, simple enough. 2x plus 3, we got it right. Alright, next one, product rule. Oops. So, these next two get kind of wordy, I guess you should call it. Just try to follow along. Basically, if f of x has the form of g of x times h of x, then its derivative, or its f prime, is equal to g prime of x times h of x plus h prime of x times g of x. Basically, you just, the two unique combinations is what this is. The one where g has the derivative and the one where h has the derivative times their original values. This one looks kind of hard to remember, but it's not so bad once you get used to it. So let's go through an example here. So, we've got f of x, this is a really easy one, is equal to 3x. We could call these two different functions. We could say this is one function, and this is another one. So we're saying that g of x is equal to 3, and h of x is equal to x. We take the derivative of each of them independently, so g prime is equal to 0, and h prime of x is equal to 1. And we put them into this formula that we figured out, or that I told you. So g prime is 0, so we get, let me write this down, f prime of x is equal to 0 times our h of x, which is x, plus g of x, which is 3, times h prime of x, which is 1. So we end up with 3. That's all, because this right here cancels. Simple enough. Let's see if we got it right. So here we have our f of x equal to 3x, and this derivative here should just be a line through 3. Yep, there we go. Okay, now we're going to do something more complicated. Let me turn those off. So, h of x is equal to x squared minus 5 times x to the 4th minus 4. Alright, let's define this right here as g of x, and this right here as, oh, we're already using h. Well, we'll call it I of x. So our derivative should have the form of, I'll write it down, so h prime of x should have the form g prime of x times I prime, or just regular I, plus I prime of x times g of x. So let's solve those out. We'll say g prime of x is equal to, this one's g. Okay, so we know how to do this one. It's the sum rule in addition to the power rule. So we have 2x, and the derivative of this is 0, plus 0. And our I prime of x is power rule, so we bring down the 4, and then we subtract 1, and the derivative of 4 is 0. So our final derivative is h prime of x is equal to g prime, which is 2x, times I of x, which is x to the fourth minus 4, plus I prime of x, which is 4x cubed, times g of x, which is x squared minus 5. I'm not going to multiply that out just because it's fine as is, but that's our derivative. It's going to be hard to see that when I fill it in, just because this is kind of a crazy function. But you can at least tell that we have an even function, x squared and x to the fourth is x to the sixth, and that should tell you that both ends of the function should end on the same side, but when we take the derivative, we're ending up with x to the fifth and x to the fifth. That means that when we click this in, it should end up with the two ends going on opposite sides of the x coordinate. Which, yeah, you have this purple going down here and this purple going up here. So, yeah, that should tell you at least enough to consider it that we got it right. All right, next one, the quotient rule. As messy as the product rule is, this one's even worse. So, our basic form is f of x is equal to g of x over h of x. And its derivative is equal to, all right, I always remember this by the mnemonic low d high, high d low. So h of x, so low is the low is the denominator. D, low d high, so derivative of the high, so that's g prime, minus low d high, high d low. So now we have g of x times the d low, or h prime of x. All of that over h of x squared. Low, d high, high, d low. All of that over low squared. All right, so let's go through our example. I'm gonna move this so we have more writing room. (3x minus 5), all of that over x squared plus 7. All right, so let's the top. We're gonna say the top. The numerator is g of x, so equals g of x, and the denominator is h of x. So our g prime of x is equal to the derivative of 3x. We did that one earlier. That's just 3. And the derivative of 5 is 0. We're using the sum rule here to determine the derivative of the whole here. So it's just 3. And our h prime of x. Alright, so this is, again, the sum rule. So we have a 2x right there. So we bring down the 2 and we subtract 1 from the power. And the derivative of 7 is 0. So we just have 2x. So, low is h. So I'm going to write this down. Low. And this is high. Alright, so we get f prime of x is equal to low d high, so we have x squared plus 7 times d high, which is 3, minus high d low, which is g of x, which is 3x minus 5, times 2x. All of that over our low squared. So we have x squared plus 7 squared. Yeah, those get messy real quick. Luckily, you don't use the quotient rule too often. Usually there's a better way. But yeah, let's go look at the graph now. We'll just do this one graphically, so we're going to turn them both on. And purple is our actual function, so let's just, so we have a number that's approaching 0 on the left. Its limit is approaching 0 as x becomes negative infinity. And we have a negative, 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 0, where it passes 0. If you notice, it passes 0 right there as well. But this, I'm talking about the slope of the line. So slope is 0 way off on the left, and then it becomes negative, 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 and it turns to 0 right here. Then it goes kind of positive for a bit, and if you notice, our slope is again positive, and it, oops, and then it sort of trails off and goes back to 0 again, just like our derivative graph, which is the orange one. All right, perfect. Let's jump to our last and most important rule. Well, last for today. The chain rule. This is easily the most often used rule. It's the rule. Almost everything you'll work with going forward will use this rule. So it's important you understand it. So let's go through it. Oops. My handwriting is getting worse as I go. F of x is equal to g of h of x. Yeah. And then it's if our function has this form, g of h of x, then its derivative is equal to the g prime of h of x times h prime of x. So this one looks kind of fancy, but it's actually not too bad to work with. Let's go with an example here, which this is a pretty easy one. F of x is equal to 1 plus 3x to the 15th. Its derivative, if we define, so let's just say that x to the 15th is equal to g of x. And 1 plus 3x is equal to our h of x. And as you can see, we have inserted h of x into g of x to make what we have here. And that means our derivative is equal to, let's go through these, g prime of x is equal to, we bring down the 15 and we subtract 1, and our h prime of x is equal to 3, because the derivative of 1 is 0 and 3x is 3. So it was equal to g prime of h of x, so that's 15, 1 plus 3x to the 14, times h prime, which is 3. So that comes out to be 45, 1 plus 3x to the 14th. That wasn't so bad, right? Let's try another example and go a little bit more complicated. But also, actually, before we go on to this next example, I want to just illustrate that this is actually what we've been doing for most of this. For example, f of x is equal to 3x. We can say that g of x is equal to 3x, and h of x is equal to 1. So we're plugging in, or it's equal to x, sorry. H of x is equal to x. And we're plugging in h of x into g of x to get 3x again. We can use the same form of the product rule to say that our derivative is equal to g prime of h of x times h prime of x. And that would give us our g prime, which is 3, and it has no this won't factor in it because it's it won't have an x in its derivative, times h prime, which is 1, which is what we would have got based off of the any number of rules we would have done already. So yeah, it's actually the product rule, or the chain rule we're using going forward, or all along. Alright, so let's do our last example here. So we've got the function g of x equal to 4 plus 5x plus 2x squared, all of that to the 7th. I'm going to turn it back on, off, so we can Alright, so g of x is equal to 4 plus 5x plus 2x squared to the 7th. So let's define our two functions. We'll use L and M. L of x is equal to x to the 7th and m of x is equal to 4 plus 5x plus 2x squared. So now it should be obvious that our function is our function g of x is L of x with m of x inserted into x. So that means that our derivative, let's solve these real quick. L prime of x is equal to 7x to the 6th, based off of the power rule, and m of x is the sum rule with a little bit of power rules involved. So we have the derivative of 4 is 0, plus the derivative of this, which is 5, plus the derivative of this, which is 4x, which is equal to 4x plus 5. That's m prime. Alright, so then with that we can solve our derivative, which is equal to our L prime with m inside of it. So that's 7 times 4 plus 5x plus 2x squared to the 6th times the derivative of what's inside, or m prime, 4x plus 5. And that's our derivative. Let's take a look at our graphs. This should not be even. Well, we'll just do it graphically. So we should have a derivative which crosses 0 right here, and it looks pretty much symmetric, but it's really negative on the left of this inflection point, and really positive on the right, which it is. It passes 0 right here, and positive on the right hand side, negative on the left. Alright, so those are it for the rules. I recommend practicing complicated combinations of them all, because we'll be using them all going forward and we won't have time to solve them out. I'm just going to be casually using them without explaining them from this point on. Next thing that we're going to do is the trigonometric derivatives, which will take us a whole video because they have a lot of algebra and limits involved with them, but they are very interesting and unique derivatives, so we'll see you then. Thanks, and if you are enjoying this series, like and subscribe.